We can rotate this pattern in 6 dimensions and see that it's quite pretty. Right now, this pattern matches our best current knowledge of how nature is built at the tiny scales of these elementary particles. This is what we know for certain. Some of these particles are at the very limit of what we've been able to reach with experiments. From this pattern, we already know that particle physics at these tiny scales, the way the universe works at these tiny scales, is very beautiful. But now I'm going to discuss some new and old ideas about things we don't know yet. We want to expand this pattern using mathematics alone and see if we can get our hands on the whole enchilada. We want to find all the particles and forces that make a complete picture of our universe. And we want to use this picture to predict new particles that we'll see when experiments reach higher energies. So there's an old idea in particle physics that this known pattern of charges, which is not very symmetric, could emerge from a more perfect pattern that gets broken, similar to how the Higgs particle breaks the electroweak pattern to give electromagnetism. In order to do this, we need to introduce new forces with new charge directions. When we introduce a new direction, we get to guess what charges the particles have along this direction, and then we can rotate it in with the others. If we guess wisely, we can construct the standard charges in 6 charge dimensions as a broken symmetry of this more perfect pattern in 7 charge dimensions. This particular choice corresponds to a grand unified theory introduced by Pati and Salam in 1973. When we look at this new unified pattern, we can see a couple of gaps where particles seem to be missing. This is the way theories of unification work. A physicist looks for larger, more symmetric patterns that include the established pattern as a subset. The larger pattern allows us to predict the existence of particles that have never been seen. This unification model predicts the existence of these 2 new force particles, which should act a lot like the weak force, only weaker. Now we can rotate this set of charges in 7 dimensions and consider an odd fact about the matter particles. The second and third generations of matter have exactly the same charges in 6-dimensional charge space as the first generation. These particles are not uniquely identified by their 6 charges. They sit on top of one another in the standard charge space. However, if we work in 8-dimensional charge space, then we can assign unique new charges to each particle. Then we can spin these in 8 dimensions and see what the whole pattern looks like. Here we can see the second and third generations of matter now, related to the first generation by a symmetry called triality. This particular pattern of charges in 8 dimensions is actually part of the most beautiful geometric structure in mathematics. It's a pattern of the largest exceptional Lie group, E8. This Lie group is a smooth, curved shape with 248 dimensions. Each point in this pattern corresponds to a symmetry of this very complex and beautiful shape. One small part of this E8 shape can be used to describe the curved space-time of Einstein's general relativity, explaining gravity. Together with quantum mechanics, the geometry of this shape could describe everything about how the universe works at the tiniest scales. And the pattern of this shape, living in 8-dimensional charge space, is exquisitely beautiful. And it summarizes thousands of possible interactions between these elementary particles, each of which is just a facet of this complicated shape. As we spin it, we can see many of the other intricate patterns contained in this one. And with a particular rotation, we can look down through this pattern in 8 dimensions along a symmetry axis and see all the particles at once. It's a very beautiful object. And, as with any unification, we can see some holes where new particles are required by this pattern. There are 20 gaps where new particles should be, 2 of which have been filled by the Pati Salam particles. From their location in this pattern, we know that these new particles should be scalar fields, like the Higgs particle, but have color charge and interact with a strong force. Filling in these new particles completes this pattern, giving us the full E8. This E8 pattern has very deep mathematical roots. It's considered by many to be the most beautiful structure in mathematics. It's a fantastic prospect that this object of great mathematical beauty could describe the truth of particle interactions at the smallest scales imaginable. Now, this idea that nature is described by mathematics is not at all new. In 1623, Galileo wrote this: "Nature's grand book, which stands continually open to our gaze, is written in the language of mathematics. Its characters are triangles, circles, and other geometrical figures, without which it is humanly impossible to understand a single word of it. Without these, one is wandering around in a dark labyrinth. I believe this to be true, and I've tried to follow Galileo's guidance in describing the mathematics of particle physics using only triangles, circles, and other geometrical figures. Of course, when other physicists and I actually work on this stuff, the mathematics can resemble a dark labyrinth. But it's reassuring that at the heart of this mathematics is pure, beautiful geometry. Joined with quantum mechanics, this mathematics describes our universe as a growing E8 coral, with particles interacting at every location in all possible ways according to a beautiful pattern. And as more of the pattern comes into view, using new machines like the Large Hadron Collider, we may be able to see whether nature uses this E8 pattern or a different one. This process of discovery is a wonderful adventure to be involved in. If the LHC finds particles that fit this E8 pattern, that will be very, very cool. If the LHC finds new particles, but they don't fit this pattern, well, that will be very interesting, but bad for this E8 theory. And, of course, bad for me personally. Now, how bad would that be? Well, pretty bad. But predicting how nature works is a very risky game. This theory and others like it are long shots. One does a lot of hard work knowing that most of these ideas probably won't end up being true about nature. That's what doing theoretical physics is like. There are a lot of wipeouts. In this regard, new physics theories are a lot like startup companies. As with any large investment, it can be emotionally difficult to abandon a line of research when it isn't working out. But in science, if something isn't working, you have to toss it out and try something else. Now, the only way to maintain sanity and achieve happiness in the midst of this uncertainty is to keep balance and perspective in life. And I've tried the best I can to live a balanced life. I try to balance my life equally between physics, love, and surfing, my own 3 charge directions. This way, even if the physics I work on comes to nothing, I still know I've lived a good life. And I try to live in beautiful places. For most of the past 10 years, I've lived on the island of Maui, a very beautiful place. Now, it's one of the greatest mysteries in the universe to my parents how I managed to survive all that time without engaging in anything resembling full-time employment. But I'm going to let you in on that secret. This was a view from my home office on Maui. And this is another. And another. And you may have noticed that these beautiful views are similar, but in slightly different places. That's because this used to be my home and office on Maui. I've chosen a very unusual life. But not worrying about rent allowed me to spend my time doing what I love. Living a nomadic existence has been hard at times, but it's allowed me to live in beautiful places and keep a balance in my life that I've been happy with. And allows me to spend a lot of my time hanging out with hyper-intelligent coral. But I also greatly enjoy the company of hyper-intelligent people. So I'm very happy to have been invited here to TED. Thank you very much.
Stay.